Hello guys, welcome to the reinforcement learning series. Today we're going to implement value iteration method using Frozen Lake. So let's begin. First we will import the packages and define constant. Import collections and of course environment name. That will be definitely Frozen Lake. Gamma 0.9 and test episodes. For now we will take 20. Now we will define an agent class which will keep our tables and contain function that we'll be using in the training. So let's create it. Agent environment, we'll create a gem make environment name. State, initially we will reset it. And rewards, we will maintain a dictionary. And serve transitions. Again we will maintain a dictionary for the basically to keep the track, like how many times a specific state agent has entered into, and of course the value. Collections default and same. Okay, so basically we create the environment that we will be using for data samples, obtain our first observation, and define tables for reward, transitions and values. Now we will create a function to gather random experience from the environment and update the reward and transition tables. And let's create it. Play, say we need to name it play and random steps. Self count for and action that we will take, that will become from action space sample, and basically whenever we will take this action in the environment, we will get into a new state. We will get a reward, the done flag, whether you reach the terminal state or not. Okay, and this will come when we take a step in the environment. So environment step action, and of course self rewards. So the current state action that we took and the new state that we entered into, that, and definitely the reward that we got. And of course we will track of transition also. That is basically state and action, the new state, and will increase the count if we enter again. And of course we will update the current state after also taking the action. If we have completed, otherwise the current state will become the new state. basically, so note that we don't need to wait for the end of the episode to start learning. We just perform n steps and remember their outcome. And this is one of the differences between value iteration method and the cross entropy method, which can only learn on full episodes. Now we'll create a function to calculate the value of action from the state using our transition reward and value tables. And basically we will use it for two purposes: to select the best action to perform from the state and to calculate the new value of the state on value iteration. So the first thing we will do is we extract transition counters for the given state and action from the transition table, and counter in this table have a form of dictionary as you have seen, and with target state as the key and count of experience transition as the value. We sum all counters to obtain the total count of times we have executed the action from the state, and we will use this total value later to go from an individual counter to probability. And then finally we iterate at every target state that our action has landed on and calculate its contribution to the total action using our Bellman equation. And this contribution is equal to the immediate reward plus discounted value for the target state, and we multiply this sum to the probability of this transition and add the result to the final action value. So it is going to be a very simple thing. So let's code it. So we will name the function as say, let's keep it simple, calculate action value. Target counts, transitions, state action, and of course total. So it is going to be sum of all the values, that is how many times a specific state is visited, keeping track of that, and finally adding them all. So target count dot values, action value initially we'll take it 0, and let's iterate. And we're going to iterate over all the key and value pairs with states and counters, and we'll take the reward, that is self.rewards, the current state, action that we took, and the target state that we entered into, and we'll calculate the value by adding reward with gamma self dot values of definitely the target state, action value so count of divided by total, and the value that we calculated, we will do the product, and finally we will return the action value. That's it. So now we'll create a function to describe about the best action to take from the given state. It basically this function will iterate over all the possible actions in the environment and calculate the value for every action. The action with largest value wins and is returned as the action to take. So this action selection process is deterministic, as the play and random steps function that we've created introduces enough exploration, so our agent will behave greedily in regard to our value approximation. So let's create this function. So it's going to be very simple code, and let's name it select action. Okay, initially we will initialize best action, best value, both as definitely none, and then we'll iterate for action in let us take a specific range of action from self environment action space. Okay, action value self dot calculate action value state action, and if best value is none, or if best value is less than the current action value, then we will update it with the current action value. So here we did it, and of course we will also update the best action, and finally we will return the best action. Okay, so basically now we'll create a function that uses this select action to find the best action to take and plays one full episode using the provided environment. This function is used to play test episode during which we don't want to mess with the current state of the main environment used to gather random data. So we use the second environment passed as an argument, and the logic is going to be very simple, and that would be already familiar to you. So let's create it and we'll name it play episode. Okay, so environment, and initially total reward will take as 0, state environment reset, action that will take, that will be the best action. Okay, and after taking that we will enter into a new state, and definitely we will get a reward and the done flag. Okay, environment step. Okay, so of course we'll keep a track of the rewards, state action and the new state. Okay, and of course the transitions also. State action and the state, now we end up into how many times we have visited, keeping track of that, and will increase the total reward by adding the current reward to it. And in case if we are done, we'll break out from the loop, and in case if we have not done, we'll continue to iterate. So we'll update the current state, the new state, and finally we will return the total reward. And now we'll create the final method of the agent class, that is our value iteration method. And what we do is just loop over all the states in the environment. Then for every state we calculate the values for the states reachable from it, obtaining candidates for the value of the state, and then we update the value of our current state with the maximum value of action available from the state. So let's create it. It is going to be very simple code. So we'll name it value iteration, and for state we'll range self environment observation. Okay, and state values and calculate action value from state. Okay, and for action that we take from a specific range, say self environment action space n. Okay, and we will upgrade it with the maximum value of the state values that we got. Okay, state, and we'll take maximum. Okay, fine. So that's all of our agents method, and now the final piece of code is going to be our training loop. So it is very simple and very familiar to you. Of course, the test environment, gym make environment name, and initialize the agent. Okay, and iteration number will take 0. Now we'll also take the best reward that will update from time to time. So let's iterate while we'll place some random steps, let's say 100, and perform the value iteration. So basically, first we perform 100 random steps to fill our reward and transition tables with fresh data, and then we run the value iteration over all states. The rest of the things we will play test episode using the value table as our policy, and then we track the best average reward and stop the training in case if we reach the best reward. So let's do it. So reward is going to be say 0.0. The test episode, that was definitely 20, and rewards that we will upgrade it, play episodes. It is going to be test environment. Of course, we will do the monitoring also, whatever is happening. So render, and in case if the current reward is greater than the best reward, we will update it and also print it, so we have a proper track on that. And let's name it best reward updated from best reward. Okay, and let's upgrade it best reward, the current reward, and in case if reward is greater than 0.80. Oops. So we're going to break out from the loop, and that will be final. So let's say solved in, we'll mention in how many iterations we solved it. So okay, we'll break out from the loop And so we are done. So let's execute the code. So it has started. So let's see. So it is completed in 27 iterations, and now we are going to study Q learning, and it is very similar, and the difference is really minor. And the most obvious change is to our value table. In the previous, that is the value iteration method, we kept the value of the state. So the key in the dictionary was just a state. Now we need to store values of the Q function, which has two parameters, state and action. So the key in the value table is now a composite. So over here, so we will use values. Okay, perfect. And the second difference is that this function, the calculation action value, we just don't need it anymore, as our action values are stored in the value table. And finally, the most important change will be the code in the agent's value iteration method. Like before, it was just a wrapper around the calculation action value call, which did the job of Bellman approximation. Now, as this function has gone and had been replaced by a value table, we need to do this approximation in the value iteration method. And the code is very similar to the calculation action value that we saw in our value iteration method. And in fact, it does almost the same thing. And for the given state and action, it needs to calculate the value of this action using statistics about target state that we have reached with the action. And to calculate this value, we use the Bellman equation and our encounters, which allow us to approximate the probability of the target state. And the Bellman's equation, we have the value of the state. Now we need to calculate it differently. So basically, before we had it stored in the value table as we approximated the value of the state. So we just took it from this table, and we can't do this anymore. So we have to call the select action method, which will choose for us the action with largest Q value, and then we take the Q value as the value of the target state, and we can implement another function that can calculate for us this value of the state. But select action does almost everything we need, so we will reuse it here. And so the main modification is going to happen in the value iteration method. So let's do it. Okay, so from here we're going to take for action self.environment, of course, action space action value target counts transition state action and total sum of the target and basically for target state count in target counts and basically items. We're going to iterate in the key value pairs. So key, that is state action and the target state. Okay, and the reward self.rewards key, and definitely the best action that will come with the select action function. So we will pass the argument as target state. Okay, and calculate the value. Sorry, reward plus gamma multiplied by self dot values, the target state, and best action. Oh, so this is the best action, not reward. I'll be going to select the best action among all the actions, and we're going to add up to the action value. Count and total. So we're going to multiply it with value, and finally self dot values state action value. Okay, perfect. So let's execute it. So Python qlearning. So it has started and it has perfectly solved in 27 iterations, and this was the qlearning method. There were few changes. It was very similar to the value iteration method. So thank you for watching the video, and please subscribe the channel.